Thank you so much, everyone, for joining. This is day 3 of the very first UC-wide Love Data Week. And this is going to be our lightning talk session from data science students or students who are not in a data science major but are doing data science projects. So the way this is going to work is we are going to have 5 minutes per lightning talk. So 5 minutes for a presentation and then 2 minutes for Q&A. So both the chat and the Q&A are open. Because we are in a webinar format, the way it will work is you can put your question in the Q&A and then I will relay it to the presenter. And we are going to keep strict on the time so that we can fit in all the presentations. So again, we'll have 5-minute presentations, 2 minutes for Q&A. If you have questions that we don't get to, I will just leave them in the Q&A and the presenters can actually type answers to those questions that we don't get to live. Okay, so I know some people are still trickling in, but to get things going, because we only have an hour and these are all fantastic projects that deserve plenty of time. Again, thank you so much for joining us. And we are going to go ahead and get started with our student lightning talks, starting with, there we go, Gil, who is going to talk about likelihood, the probabilistic data quality engine. So Gil, go ahead.
Hi everyone. My name is Gil. I am an applied math student at UCSD, and today I'm going to be talking to you guys about my project. So if you're a practitioner in the field of data science or looking to become one, I'd like to start off with a statement you could probably relate to. Your data really, really sucks sometimes. It is commonly said that 60 to 80% of a data scientist's time is spent just cleaning data. To put that into perspective, if a project takes 10 days, 6 to 8 of them are going to be spent just going through data, tidying it, and finding outliers. Contrast that with only a day where you get to do that cool machine learning stuff, and the 4 minutes you spend building your data visualizations, and you get a very major question. Why does it take so long? One of the reasons is that you don't always know what to actually look for. There are about 1.5 million things that can go wrong anywhere in the so-called data science process, most of which you'll end up banging your head against a table for an hour for not having seen earlier, and the others which may not be so trivial. Take, for example, the recent Excel fiasco, where scientists were actually forced to rename genes to prevent Microsoft Excel from reading them as dates. To make things worse, this problem is only exacerbated as your data stops looking like this, next slide, and starts looking more like this, next slide. You can move on to the next slide. Okay. Now, given that data science is a really resourceful field, a lot of work has been done to provide some Tylenol for this headache and also potentially save the field of computational biology. I'd like to give a particular shout out to the open source project Great Expectations that really bolstered the effort. It's a contributed unit test called Expectations for Your Data and allows you to validate your data assumptions. As a small disclaimer, I also work for these guys. Now that I've wasted half my time just motivating why data quality is a major problem, I'd love to show you what I actually built. My project, built this summer with the help and mentorship of Professor Colin Jamont, is named Likelihood. The project is so named because it utilizes several machine learning methods to estimate the likelihood, or the chance, that a value is truly an outlier. It does this using some machine learning and statistical transformations to compute the distribution in regard to different factors that may potentially make an outlier. Data density, data variation across holidays and days of the week, and common string patterns. This distribution was then used to compute entropy, or in other words, how chaotic a data is. The primary advantage is this. Instead of making deterministic yes or no judgments about whether points are outliers and missing some of them entirely, we can now deal with them in the realm of probability and know which data to be on the lookout for. Next slide. Now, instead of boring you guys with deep details, I thought I'd show you guys a quick demo. Couldn't find any big data for this demo, so I decided to take 10 rows of data and just make them very big. But as we can see here, we have a column of emails, a column of professions, and a column of the city of San Diego, California. If we look through the column, everything seems to be fine until you get to row 32, where some some person accidentally typed an exclamation mark instead of the at. Using string patterns, likelihood has captured this outlier and assigns it an entropy of 12.23. We go through the professions. People are DJs, doctors, nurses, programmers, and then someone decides to put that they're a star. I'm sure they are a star, but unfortunately that's not a profession and thus is assigned an entropy for 52. We can find a similar blunder on line 38 where someone just barfed all over their keyboard, and these are found to be outliers as well. Next slide. All right, before I finish my talk, I thought I'd say something about how I actually got my data. I used many data sets in testing my model, most of which were stolen, taken from the city of San Diego. There are plenty of these data sets, and they can also be downloaded as CSVs. As far as data cleaning itself goes, I did very minimal cleaning with the exception of dropping certain untested data types, as I wanted likelihood to find the errors itself. I would recommend building your own synthetic data sets for actually testing your models, however, as they let you know what assumptions you actually need to validate and give you an understanding of what should actually be happening. Next slide. I'd like to end on an optimistic note, as I think the future of data quality is very bright. I believe projects such as Great Expectations, among others, make massive strides in ensuring that we can trust our data and know what to expect from it, a mission I'm proud to be a part of. However, with the size of our data warehouses growing exponentially, I'd like to advocate for further bolstering this effort. At the very least, I hope likelihood has given you a glimpse of what is possible when those 6 to 8 days are automated to be no harder than those 4 minutes you spent on data visualization last week. Thank you.
Thank you, Gil. That was fantastic. So now we have 2 minutes for questions. Feel free to put your questions into the Q&A, and I see we have one already. Okay, so you mentioned multiple machine learning models were used in this project. Do you mind specifying which ones you used?
Not at all. So for data density, a good one for measuring where outliers are in terms of actual density and seeing that less dense areas are counted to be outliers, I use kernel density. Then for another one I used extensively was principal component analysis, which is PCA. For value counts, I used bootstrapping. For time series and outliers based on holidays and days of the week, I used a model called Facebook Profit. And then I also sort of invented one for string patterns that was based on Claude Shannon's paper, A Mathematical Theory of Communications. And that one just used string patterns to find outliers.
Fantastic. We do have another question. Would a random cut forest be appropriate for this application?
A random forest is an interesting application and something I actually considered extensively. With any decision tree type algorithm, you get interpretability, which is a very good thing when it comes to outlier detection. However, you're not exactly making the decision based on a particular factor that may make an outlier. So I would say that it is very good as a way of understanding how the model actually finds that separation between outliers and non-outliers, and it's particularly good as a visualization tool. So if you choose to make a data viz with a random forest, I believe that would be very appropriate for something like this.
Perfect. Gil, you are spot on timing. Thank you so much. So we're going to move on to Arnav Gupta, who is going to talk about this fantastic project, the legacy of redlining.
Hey everyone, my name is Arnav. I'm currently a sophomore at UC San Diego, and I'm going to talk to you now about my project called Quantifying the Effect of Redlining on Racial Segregation in US Cities. Next slide. So let's first start with some brief motivation. What you're looking at here is a map of the city of Cleveland from back in 2010, and every dot you see on this map represents one person who responded to the 2010 census. It's color-coded by race, So green corresponds to African American, blue corresponds to white, other colors correspond to the other races listed on the 2010 census. And the immediate first thing you can see is that there's a very clear disparity between where Black Americans live and where white Americans live. You can see like a very clear east-west sort of split. But now if I overlay this map on top of it, next, you can see that this was a map that was drawn back in 1938. So 70 years prior to that first map you saw. And you can see that the colors on this map match up almost perfectly with the colors that you see on the previous map. So what I'm going to try to do in this talk is explain why this sort of feature exists and what we can use to quantify it. So next slide, please. So what is that map that you just saw, the second map? It's what's called a Holk redlining map, which is a map drawn by the federal government in 1938 as a method of allocating where home loans should be allocated to during the Great Depression, when obviously there was a sort of squeeze on the amount of capital allowed for home mortgages. So what happened here was a lot of mortgage surveyors at a lot of banks, and especially at the federal government, decided to use superficial attributes, things like race or class, to essentially signify where people were living at different times and justify different neighborhoods as being of different characteristics. So red neighborhoods would be considered high likelihood of minority appeal, and then essentially blue or green neighborhoods were considered high likelihood of white appeal. And these superficial attributes were used to justify segregation into different neighborhoods across many different cities in the United States. Then step two of this process was then these maps could then be used by private banks to offer unequal resources to each of these neighborhoods and sort of use this as a foil for discrimination. Say, no, we're not actually being racist against you. We're just sort of being discriminatory based on your neighborhood because we think your risk likelihood is a lot higher than it should be. And what this effectively did was it separated races of people into different areas of cities, creating things like parallel lives and ghettos and a lot of the problems that we see in today's modern urban landscape. Next slide. So in this study, I'm going to seek to answer two key questions. The first is whether these Holk redlining maps are still relevant in describing racial segregation today. And then if so, can we quantify to what extent this is true in various cities? So the methodology, the star of the show here is this process called Markov chain Monte Carlo. Basically what it is a Markov chain stochastic process combined with a Monte Carlo form of analyzing the results of that stochastic process. It's really useful in situations where the sample space is so large that we cannot randomly sample from it effectively or efficiently. So what you're seeing here is a brief demo of what's going on. On the left side is a map of Oakland, California, which is where one of the first redlining maps was ever drawn. And what you're seeing is a Markov chain Monte Carlo map sort of iterating on a process which cuts the city into various different districts. So it started with the Holk redlining maps, and then it iterates on the cities one by one. It iterates on these districts, sort of making sample cuts of what the city could have been under sort of like counterfactual maps. From each of these maps, we then compute a score known as the entropy score, which basically signifies essentially the level of segregation that would be present under that specific method of segregating the city. And then what we do is we take all of these numbers and we put them on a distribution. But we take that first distribution, which remember comes from essentially the Holk redlining maps, and we plot it on the distribution. We sort of try to get two quantities from this. The first quantity that we can get from it is sort of similar to what a p-value is. Next animation. And that's basically essentially the likelihood that that first number actually belongs to the distribution that we saw. And then the second number we get is essentially the spread between the mean of the distribution we saw and the first number. So we have this test statistic and we have a distribution, and we can use this to learn a lot of things about the nature of these Holk redlining maps. Next slide. So I'll skip over most of the methodology section and move straight to the results. What we're seeing here is we ran this on essentially 11 cities across the United States, and we got this distribution, and we also got the test statistic. What you're seeing here is essentially all of these different distributions for all the different cities plotted on the same plot, and they're all normalized to 0. So imagine that line at 0 being that first test statistic we talked about in the previous slide, and then all of these distributions are there. The really cool thing about this slide is that it's very, very indicative that in all of these cities, we saw a very, very large causative essentially link between the Holk redlining maps and the current levels of segregation today. In other words, no map of the millions of maps we were able to draw in all of these cities was better able to describe current levels of segregation than the maps that were drawn in 1938, which is kind of insane when you think about it. Those maps were drawn 70 years prior, and they still hold so much power over the way we live today. Next slide. So the second thing we can do is use that second bit of analysis to actually compare between the different cities, we look at the spread between the mean and the test statistic, we can see that Detroit seems to have the largest spread between the mean and the test statistic, and Chicago seems to have the least, which tells you a little bit about how far the Markov chain's mean moved from the test statistic. Next slide. So there's two main key insights we get from here. The first one is that in all of these 11 cities, the Markov chain Monte Carlo maps show that the essentially the Hoek redlining maps drawn in 1938 were very, very indicative of the current levels of racial segregation. That's the first key insight. The second key insight is that there's significant variation between cities. Like we saw in the previous slide, these Hoek maps were better able to quote unquote predict segregation in Detroit roughly 6 times more accurately than they were to in San Diego. Next slide. So why is this useful? I think when most of us think of redlining maps, we automatically know that they've been discriminatory and that they're still discriminatory today. So why is this useful? Well, the first thing is it provides a very strong argument for situations of reparations or reparative justice. But the second, and I think far more powerful significance here, is what I like to call legislative benchmarking, which is to say that we can actually use this sort of test and run it after different policies are placed in different sections of cities to see whether those policies are actually producing things like equal housing outcomes. So for example, the Equal Housing Act of 1970, what we can do is we can, if we were to, for example, instantiate a similar policy today, we could run this test before that policy, before that same equal housing policy is put in place, and then run it again maybe 10 years after that same equal housing policy is put in place. And we can look at the difference between those two results and figure out, is this policy actually producing equal housing outcomes or not, which I think is really good. But more importantly, what I've described here is more of a methodology than it is really like a particular type of test, which means that it's very modular. You can take things like, you can swap a lot of things out. So you can swap out the test statistic that you're using, you can swap out the distribution that you're using, you can even swap out things like the specific outcomes. You can look at income statistics, for example, rather than race, which I think makes it really powerful. So that's the conclusion of my talk. If there are any questions, I'm happy to take them now. But a couple of things I want to point out. I got the data from the IPUMS project at University of Minnesota, and this whole project was heavily inspired by the metric gerrymandering and geography project over at Tufts University, led by mathematician Moon Dushan. Thanks.
So thank you so much. We ran a bit long, but considering that is putting a year's worth of work into a very short time, that was amazing. If you have questions, feel free to drop them into the Q&A. We won't answer them live, but all the panelists have access to the Q&A, so they can answer it there. So next, we are going to go to Advitya, who's going to talk about this amazing project.
Thank you. Hi, my name is Advitya. I am a senior data science major, and I'll be presenting my lightning talk on hyperparameter optimization for deep neural networks with Apache MATLAB. Next slide. So various enterprises today use Apache MATLAB, which is an open source machine learning library for scalable in-database analytics, which refers to analyzing big data while the data resides inside the database itself. And in-database analytics has a variety of advantages related to scalability, networking cost savings, security, etc. MATLAB is especially designed for massively parallel processing, or MPP databases, dealing with petabytes of data, and also pioneered deep learning for database resident data. Next slide. MATLAB, for its deep learning infrastructure, adopted model hopper parallelism, a novel parallel HEG execution approach formulated in the research lab I've been involved in. However, MATLAB did not originally support any fully automated methods for hyperparameter tuning on top of its MOP infrastructure. And one of the biggest challenges with deep learning is identifying the right model architecture and hyperparameters, as training deep nets is a highly time and resource intensive process. Next slide. Hence, I implemented grid search and random search, two of the most widely used strategies for hyperparameter tuning. Grid search is a brute force algorithm that evaluates all configurations in a discrete search space, but is extremely slow in high dimensional search spaces. Random search randomly samples configurations to evaluate and can work in discrete or continuous search spaces. Random search has been proven to find as good or better models with a fraction of the resources as grid search, but suffers from high variability in performance and can still be resource heavy with large and complex search spaces and workloads. Next slide. For faster model selection, I implemented AutoML methods such as Hyperband, which speeds up random search with adaptive resource allocation and successive halving. Hyperband takes two inputs: R, the max amount of resources allocated to a single configuration, and eta, the proportion of configurations discarded in each round of successive halving, which is also called a bracket. Hyperband explores and evaluates parameters by training them under fixed resources and exploring the more promising configurations with more resources to find the best configurations. Hyperband starts with the most aggressive bracket to explore maximum configurations and ends in the final bracket, where every configuration is allocated R number of resources. Hyperband has been initially shown to speed up random search by up to 70x. In the case of implementing Hyperband in MATLAB for analytical MPP databases, I introduced a novel optimization of allocating the rounds of these brackets diagonally to various record nodes to take advantage of distributed compute and storage offered by such databases. This means that instead of running each bracket one by one, this method would simultaneously start the first iteration of the next bracket with the next iteration of the current bracket to allocate all iterations to various machines diagonally, and so on and so forth. Next slide. After implementing Hyperband, I also added support for HyperOpt as part of an additional AutoML capability. HyperOpt is technically not an algorithm, but a Python module supporting random search and TPE for performing hyperparameter optimization over awkward search spaces. TPE is sort of a Bayesian optimization approach, which has this intuition of setting some sort of a prior belief of the best model configuration and intelligently explores a search space by narrowing down to more favorable directions where the best model configurations can lie. Next slide. Here are some of the APIs I built showcasing how users can declaratively specify all details about their workload and have MATLAB do all the heavy lifting in terms of scheduling and executing the workload, providing meaningful status update messages, and valuable workflow details. Here, I use the optimized Hyperband feature I implemented with the C410 dataset, which is an open source computer vision dataset for object detection. And users can also draw some pretty cool loss curves to visually observe how certain badly performing configurations were interrupted early on during training and vice versa. Next slide. In summary, I got to build features to have MATLAB automate and optimize the entire deep learning model selection process end to end. This would speed up the exploration of model configurations and accelerate the workflow and productivity of data science and deep learning practitioners while using MATLAB on top of MPP databases, analyzing petabyte scale volumes of data. Next slide. All the features I've talked about will be released in the next version, and these contributions have made me one among 57 and one of the youngest contributors of Apache MATLAB in the world. Thank you for listening, and I'm happy to answer any questions.
So I hope everyone is extremely impressed. We're only 3 talks in, and these are amazing. Again, feel free to put questions in the Q&A. Even if we don't get to them live, the presenters can answer them. So I do have a question. I'm not remotely qualified to comment on the technical details, but I am super curious why you got so involved in this. You said you're one of the youngest contributors. So how did you even start working on this MATLAB project?
Yeah, so essentially the research lab I've been involved in was kind of also closely interacting with the industry in terms of like a team which was working at VMware on this project. And this was an open source project, of course, and they were also kind of pretty motivated by some of the research work done in the lab I've been involved in. And essentially, they were kind of also looking at advanced like model training infrastructure methods to sort of accelerate deep learning approaches. At the same time, the team working on this library was kind of more focused on building these deep learning capabilities. And a lot of the processes for the model selection process for finding the best model architecture and hyperparameters was still a painfully manual process in some sense. So essentially, I kind of found a pathway where I believe that I could sort of also build some features which could sort of automate and accelerate these kinds of processes end to end on top of the pre-existing infrastructure. So that's how I kind of got interested and involved in it as well.
That's fantastic. And it's amazing to see you getting involved in some of the open source. It is one of the kind of most open ways to get involved with software development because anyone can submit a contribution. So thank you so much. That's really interesting. So next up, we have Ted, who is going to talk about the bubble analysis of the NBA. So Ted, go ahead and take it away.
Hi everyone, my name is Ted. I'm a second year applied maths major, and this is my analysis of the NBA bubble. And in case you don't know, the bubble is due to the pandemic last year, NBA suspended season and they restarted season in an isolated place and has all the useful facilities. And today I'm going to explore how the players perform in this isolated environment that has no cheering crowds or home court advantage or anything. And I got my data from nba.com/stats using Python and this useful API wrote by Swar Patel. And all the data are from the last season, which is 1920 season. And since all the data from the official NBA website, there are no missing data, and they're all pretty well organized. And I only included the players who played both inside the bubble and outside the bubble, which is a total of 309 players. And here's a sample of what the data set looks like. And here is a graphical distribution of the points per game. The blue line is points per game of the players inside the bubble, and the orange line is the points per game outside the bubble. And you can see the two distributions are pretty similar. And I ran a t-test, got a value of 2.2196, and which indicated that there is no significant difference in between these two distributions, which is interesting. I did the same thing for the field goal percentage, and I got a similar result. There is no significant difference between these two distributions. Next slide, please. I did a similar thing for average 3-point percentage. Although you can see on the graph, the distribution in the bubble has a higher standard deviation, but the t-test suggested there is no significant difference between these two distributions. I did the same thing for average free throw percentage and amount of rebounds, amount of assists, and average turnovers, and they all suggested there is no significant difference between the two distributions. And next slide, please. So based on my result and graph, they all indicate that the players' performance are pretty consistent in inside and outside the bubble. And the difference in standard deviation may be a result of the players playing more game outside the bubble than they played inside the bubble. Next slide, please. Then what about Paul George? Paul George was one of the most criticized players last year. And 2 seasons ago, he was one of the MVP candidates. But last season, he became Pandemic P. Next slide, please. And same thing. I got data from NBA.com, and I collected all the games he played from the last season, which is a total of 42 games he played outside the bubble and 19 games he played inside the bubble. I grabbed, this is a points distribution of Paul George, and again, blue line is inside the bubble, and orange line is his stats outside the bubble. And I did a t-test, which says that there is no significant difference between his performance in and outside the bubble. And next slide, please. I did the same thing for him for his 3-point percentage, which also suggested that there is no significant difference between his 3-point percentage inside and outside the bubble. Next slide, please. Then this is a analysis of his plus or minus. Two graphs are pretty similar, and the t-test also suggested that there is no significant difference between his performance. And next slide, please. Again, shockingly, the test also suggested that his performance was pretty consistent throughout last year. Then why are people criticizing him? That's weird. And that's my next step. I'm gonna find out why are people criticizing him. And another thing I'm gonna do is, one bias I may have in my data is that the games played inside the bubble are more intense than the games played outside the bubble, since those are the majority of the games played inside the bubble are playoff games. So next, I'm gonna compare the playoff games played inside the bubble with playoff games played outside the bubble in playoff games in the previous seasons to see if there's any difference between them. And yeah, that's it. Thank you very much.
Thank you, Ted. And extra thanks to Ted because he met with me right around the time I was putting together the Lightning Talk series. And I very strongly said, hey, Ted, this analysis would be great as a Lightning Talk. So he's been really great about it. So I'll pause in case anyone has any questions for this. I know a little bit more about the project, so I don't want to ask any particularly leading questions, but I am interested, Ted, we talked a bit about this before, but so why the NBA bubble? It's a great, it's a great personal project, but why the bubble?
Yeah, like first off, I'm very interested in data science and sports. This is like super cooperative to combine two fields I love. And another personal reason is that I'm not a fan of the Lakers roster right now, so I really want to discredit their championship they got last year. So I'm gonna try to find some clues, or I want to prove that players perform worse in the bubble, but I can. Well, their championship was legit, so yeah.
I mean, I will say trying to prove that something isn't working is a great motivation, and yet sometimes the data just doesn't turn out the way we want. But thank you, Ted, so much again. Oh, There's a question that you can answer in the chat of how many games will the
I don't-
Clippers win this year?
I don't know. I'm not sure, to be honest. Well, they're doing much better than last year, but yeah, I'm not sure.
Fair enough. All right. Okay, so we are going to move on to Bailey Mann's analysis of Arctic sea ice. So go ahead, Bailey.
Hi, my name is Bailey Mann. I'm a fourth-year data science major at HDSI, and this is my project that I've been working on this quarter with my mentor, Dr. Zaslavsky. Next slide, please. So first, I'd like to give a little bit of background information on the subject area. The Arctic Circle describes a circular area around the North Pole, one that's marked by the ability to not see the sun during the winter solstice when you're above the circle, which is approximately halfway down this global line. And within this circle, there exists an ever-changing coverage of glaciers and ice flows that expand and contract with the seasons. There are many factors that go into simulating and measuring these changes, such as the atmospheric conditions, the shape and size of the glaciers, both above and below sea level, and on a longer time scale, the effects of climate change. And with these changes and with current recent developments in terms of new satellites going up and more data being available, there are many resources and opportunities for getting involved with this general domain. Next slide, please. So the existing resources primarily come through the National Snow and Ice Data Center, or NSIDC, which currently creates and produces several different products from satellite data, such as the Sea Ice Index, which is a collection of shape files and images gathered from sea ice concentrations. The primary method of doing so, which is taking images and dividing them into a grid. And if some percentage of that grid, I believe it's 15%, is of a certain color, they determine that it's ice, and so on and so forth. I can go into a little more detail about it later in the questions, but to save time, we'll keep going. Another product that they create and maintain is MAISY, which is stands for something similar, which I somehow forgot to look up. I'll come back to that. It provides a slightly more accurate view of the ice on a daily basis, but it comes at the expense of consistency and trends over longer periods of time, and so it's mildly less useful for my particular purposes. There are other organizations, for example, the National Oceanic and Atmospheric Association, or NOAA, which also maintain projects related to polar ice, such as this prediction model in the bottom right here, which is shown in red. Next slide, please. I originally began brainstorming this project near the end of last year, but after hearing about the planned launch of the Sentinel-6 Michael Freilich satellite, which you can see in the top right, which will take over the current existing satellites' efforts to track sea level rise around the globe with more accuracy, and especially with relation to climate change. It's also going to focus on coastlines to a better degree to help focus on disaster prediction. The new satellite, in addition to existing data sources provided by satellites such as IceSat or Operation Icebridge, which was a NASA project to send LiDAR altimetry aircraft over various glaciers in the North Pole in order to verify satellite data to particular levels of accuracy. There's quite a few projects which have been wrapping up in, I believe, Operation Icebridge ended in 2019. IceSat went up in sometime in the last 5 years. So essentially, the field is just beginning to become available to data science, and I find it particularly interesting. Next slide, please. So what I'm working on this quarter is endeavors to produce visualizations of the changing ice sheets and various projections of the planet, similar to the one that you can currently see here. So the idea being that in order to show to a human what the change is like over large scales of time, rather than just going through a few months like this is, the idea would be to go through the last 30 years of satellite data that currently exists and attempt to verify whatever whatever patterns we can see in terms of the new data that's going to exist from the Sentinel-6 satellite. So the currently existing data, sorry, back to the previous slide for just a second. I'm almost done, I promise. There are two different algorithms that they use to gather this data, which is one developed by the NASA team and one called the Bootstrap algorithm, which is also developed by NASA, but is slightly better for calculating the edges of the ice sheets because it can deal with surface ice and previously melted ice and other interesting things. And the last step of the project for this quarter would be to visualize it in a web app or website. Next slide, please. So for future quarters, and what I would like to go to doing in the future in this project would be to create predictive modeling for it. So the first step to doing so would be to just creating a predictive model from the images and from the shapefiles that already exist to try and predict smaller areas of ice flow during the summer, especially in terms of the extent to which the glaciers will reach, to especially help shipping lanes and such. But more importantly, it provides the first step to adding in the climate model, which actually takes into account atmospheric conditions and the currents under the glaciers and the size and shape of them and how they carve and many other things, which are going to provide a more accurate model for predicting the level of ice in the future. Next slide, please. That's about all I have today. I'm here to answer any questions. Thank you for your time.
Thank you, Bailey. And I'll let people take a moment to digest and put questions in the chat. But I personally love this project. I think it's such a fantastic example of data science methodologies really being able to be used on all manner of data, especially something like a decline in sea ice that is incredibly important. And additionally, as we're going through, if we don't get to any questions or you think of them later, I know we're going through a lot of information really quickly. If you throw them into the Q&A, all the panelists can answer them there as well. So I have a quick question then. So you mentioned using satellite data. And so for those that have never worked with NASA data, could you talk a little bit about what format that kind of satellite data comes in?
Well, it comes in various different formats, actually. It's provided both pre and post-processing. So they provide it in terms of pre-downloaded CSV files and shape files, which have the pure measurements of the concentrations of ice on various days and months and weeks. But they also provide the data post-processing, which is they go through various masks and fill in holes in the data, because the satellite data that they've gathered and provide comes from various different ones which don't technically orbit in perfectly circular patterns around the North Pole. So they take this data and stitch it together essentially to create a better projection or mapping of it, which can essentially be read as a grid format through the CSV file. Most of this is explained in much better format just on NSIDC, and I can give the link to anyone who wants it better explained to them. But in essence, it provides it in various formats and also has a relatively easy to read guide on how the masks are applied and what kind of math they use. Regardless, it's relatively interesting.
Thanks, Bailey. Yeah, I really love that example because it really goes into kind of the pre-processing steps, and then of course the importance of reading the documentation online. All right, so continuing our Fast and Furious Lightning Talk series, this is our final one, and then we will have additional time for questions, but we have Zhaoyi and Yifei who are going to talk about this extremely unbalanced text corpus. So take it away.
Okay. Hi, everyone. My name is Joey, a current senior data science student at UCSD. Today, my teammate Ife and I will be presenting our project, USPTO Patent Application Prediction. This project is guided by Xiaochen and Vish from Reddy School of Management and Professor Shang from UCSD CSC Department. Now, let's welcome Ife to introduce our challenges and motivations.
Sure, thanks, Joey. Whether or not a patent application will be approval is a significant question for the patent applicants. Therefore, it is natural to develop a model to predict the approval of a patent application before submitting it to the USPTO Bureau. However, there is currently no existing product or scientific research that gives a plausible solution. This is mainly because of the following reasons. Firstly, the gigantic text corpus of past applications for both approval and rejected ones. Second, the highly unbalanced data set. Actually, around 80 to 90% of the patent claims are approval, so we can see how unbalanced that is. Thirdly, the approval of a patent claim usually means the claim is different from all the previous one. This is different from our traditional machine learning object, which tries to find similar item. So to tackle those issues, we implement an effective pipeline that includes a customized BERT model and handcrafted innovative features. Next slide, please. In total, there are around there are around 0.1 billion claims and 1 million applications. So our dataset contains the USPTO application spanning all the way from 2013 to 2019. So in our tasks, we have two sets of labels, 101 and 102. Both of them are binary values, either 1 or 0. 101 is our abstract level target, meaning if the abstract is accepted or not. And 102 is our claim level target, meaning if the claim is accepted or not. So having dealing with such a huge unstructured data set, we have to pay attention to two things, filtering and transformation. So for filtering, our goal here is to create a compact version of a structured data set. So we ingested the data into CSV files and filtering out those invalid data entry while keeping only the valid abstract, texts, and application associated features. And also for transformation, we implement a batch version of data ingestion pipeline that enable to write multiple rows of data instantaneously. So save us a lot of time. Slide, please. So this is a diagram that shows how we actually process the features by different data types. There are mainly 3 types of features, along with some possible pending features available for us to mine. So we have text data, numerical data, categorical data. So we have to deal with those categories with different methods. So for the text data, we need to throw all the text to our BERT encoder, and we have to standard scale our numerical data by z-score. And also we needed one hot encode our categorical features as well. So after doing all those cleaning and pre-processing, we then pass all the clean feature to our model and then generate predictions and evaluate our model accordingly. Next slide, please.
Yeah, now I will be introducing our model. As Aoife mentioned, there are 2 main groups of features from the USPTO database, the text feature and the application feature. In our model, we use both of those 2 features together with the similarity features that we manually calculated. I'll get to that just in a little bit. In total, there are 3 main kinds of features in our model. The first and most obvious one is the text feature from claims and abstract. They are fed into a pre-trained language model called BERT. That basically transforms the text into meaningful vectors that we can do math with. On the other side, the application features and manually calculated similarity features are then combined into a unit vector, which later combine with the BERT output to form a comprehensive representation of the patent claim or abstract. This representation vector will then go through an optional regularization, which I'll get to that in a later portion as well. Then we'll finally have our prediction of whether or not this claim or abstract will be approved. Next slide, please. As Aoife just mentioned, there are 3 main challenges. He talked about the first challenges, and then I will address the second one and the third one. The second challenge is the extremely unbalanced data. As you can see here, both 101 and 102 are super unbalanced. For 101 label, 93% are positive instances. For 102 label, 85 of them are positive. This essentially makes it really hard to teach the model to identify a negative sample. The way to tackle this problem is actually pretty straightforward. First, we use a weighted loss function to better capture the prediction loss on the minority clause. Second, in the later course of a project, we switch to AUC from accuracy as our main metrics. Next slide, please. Yeah, the last but not least, our third challenge is that we encounter is the novelty nature of patent application. As Aoife mentioned, the approval of a patent essentially means that it is different from every previous patent in the past. Therefore, our model should capture the uniqueness of a patent application. The way we tried to accomplish that was to calculate the similarity feature I mentioned in the model part. The way we calculated that was to use the BERT language model again to transform the text into vectors and then calculate the distance between those vectors and existing pattern as their similarity score. With those numerical scores, our hypothesis was that claims or abstract with high similarity scores are more likely to be rejected. Another part that's related to the similarity is the optional regularization in the last part of the model. You will basically enforce the relationship between similarity score and the prediction by assigning lower chance of approval to the claim or abstract that were highly similar to previous ones. Next slide, please. Based on all the previous work we've done, Our current model achieved the following performances. As you can see from here, 101 label or the abstract level prediction is much better than 102 prediction. Therefore, our next step in this project is to improve 102 prediction, especially in the AUC score. And next slide. Yeah, that's actually all our presentation. I hope you like it. And then we're gonna take questions.
Thank you so much. Fascinating to see a giant unbalanced text corpus like that. So again, please throw any questions into the chat. In the meantime, I'm curious what your next steps are going to be for this project, since it's such a rich data source. What else are you planning to do with it?
There are a lot of directions. The primary directions, I would say, we're gonna further, as Joey said, we're gonna further investigate the AUC matrix, and we probably gonna try more complex models, apply more layers, and also try to search the database and see if it's possible to find more available features. Because there are a lot of informations in the database waiting for us to explore.
Yeah, it sounds like there's a whole bunch of other rich characteristics that you could explore in the future and test out different models, and we'll be eagerly awaiting it. So that concludes all the talks that we had today. With that, again, feel free. We do have a little bit of time left. I always leave a bit of a buffer because you never know what technical difficulties you might be having. So feel free to put any questions you have for any presenters into the Q&A. And in the meantime, I will just say I sincerely hope you enjoyed these lightning talks. This is only a small sampling of some of the projects, the data science projects that students are working on. All these students are at UC San Diego, and we saw the range of data, text data, numerical data, census data. These are a huge range of data sources. And these are projects that may or may not have faculty presence. They might just be something that someone's working on. So I think it's such a good example of the projects that we have, especially here at UC San Diego. So again, feel free to throw any questions you have in the Q&A box for any of our presenters. And in the meantime, then, this is also the very first UC-wide Love Data Week we've ever done, which is a collaboration among all the UC campuses. And second, this is the first lightning talk series we've had for data science students. So personally, and on behalf of the students, we would love to get any feedback you have. Feel free to throw in the chat if this is something that you would like to see again on a more regular basis. I will go ahead and put my email in the chat as well. Again, I am Stephanie LeBou. I am the data science librarian here at UC San Diego. If this is something that you'd like to see more of, please feel free to let me know. I know the students are always looking for opportunities to share their projects. And as someone who has worked with many of these students, I'm always looking for more avenues for them as well, because I love seeing what everyone is working on, the interesting data problems that they have, and all manner of issues that they run into working with some of these large public data sets. So thank you so much for attending. If no one has any Q&A, I know it can be a lot to process. 5 minutes per talk is not a lot of time to digest. Again, all the presenter names are up here. You can also contact them individually. If you forget their names, but you remember my name, you can email me and I can put you in touch with the presenters. And with that, I will stop rambling, but thank everyone for attending this Lightning Talk series at UC Love Data Week. And if you get a chance and you haven't already been enjoying our other events, hopefully you can attend some of the other presentations for UC Love Data Week as well.